Hi, in this video we solve problem 9.105 from the book Thermodynamics in Engineering Approach, Cengel 9th edition. Here the statement of the problem: a gas turbine for an automobile is designed with a regenerator. Air enters the compressor of this engine at 100 kilopascal and 300 centigrade. The compressor pressure ratio is 8. The maximum cycle temperature is 800 centigrade and the cool airstream leaves the regenerator 10 centigrade cooler than the hot airstream at the inlet of the regenerators. Assume both the compressor and the turbine to be isentropic. Determine the rate of heat additions and rejections for this cycle when it produces 115 kilowatt. Use constant specific heats at room temperatures. These are the answers that is asked in the statement. This is a simple schematic diagram of the gas turbine with regenerator installed. The process starts from 1. The 1 to 2 is isentropic compression process that require work input in order to run this compressor. So in process 2 to 3, the cool gases get heated with the interaction of the hot gases that is coming out from the turbine. Then 3 to 4 is constant pressure heat addition process. Then 4 to 5 is isentropic expansion in this turbine, and it will give you the work output. Remember, at 4-stage high temperature, high pressures gases will observe, then it is expand in the turbine that will give you the work out. And the gases that is coming out from the turbine is sent to the heat exchanger, that is basically the regenerator that deliver heat to the cool gases, and then it is sent to the process 6 to 1 that extract heat to the environment at a constant pressure. This is the simple explanation of this regenerator gas turbine cycle. I hope you understand. If still there is any confusion, you can ask in the comment section. Now let me draw its TS and PV diagram of this gas turbine with regenerator. First I will draw the PV diagram. 1 to 2 is isentropic compression. This is 1 to 2. Then 2 to 3 is also occur at a constant pressures. Then 3 to 4 is constant pressure heat addition process. Here heat addition is occur, that is Qn, that we need to calculate how much heat addition is occur. And then isentropic expansion 4 to 5. And then 5 to 6 is again exchange of heat occur at a constant pressure. And then 6 to 1 is constant pressure heat rejection process. Here Q out 6 to 1, the process where heat rejection is occur, that is Q out, that we need to calculate. So what is our requirement in the statement? That is Q dot in, how much heat is supplied, and Q dot out, and how much heat is reject. Remember, the pressure P2 must be equal to P3, P4. Similarly, the pressure P1, P6 and P5 all are on the same line at a constant pressure. Let me draw the TS diagram. First is isentropic compression 1 to 2, then exchange of heat at a constant pressure 2 to 3. And 3 to 4 is constant pressure heat addition process. When heat is added, the temperature is obvious that will increase, so the maximum cycle temperature is at T4 we will observe. Here is Qn, then isentropic expansion in the turbine, it will give you the work output. Here in the compressor, the work input is required in order to run the compressor. Similarly, here is also work input, and here the expansion in turbine occur, this is work out. Then again exchange in heat transfer at a constant pressure, that is 5 to 6, and then finally 6 to 1 is heat rejections to the environment, the constant pressure, that is Q out. Now come toward the statement. What is given in the statement? Initial pressure P1 is 100 kilopascal, T1 that is 30 centigrade, compressor pressure ratio is 8, so it is equal to 8, and that is also equal to P2 divided by P1, also it equal to P4 divided by P5. Our pressure ratio is given, that is 8, and we can say that P2 is 8 times of P1, that will be equal to 800 kilopascal, because P1 is 100 kilopascal. When you multiply with 8, it becomes 800 kilopascal. Consider this statement now. The cool airstream leave the regenerator. The cool airstream that leave the regenerator is T3, is 10 centigrade cooler, so it is 10 centigrade cooler. We will add 10 centigrade with it, that becomes equal to the hot air stream at the inlet of the regenerators. This is the hot air stream at the inlet of the regenerator, that is T5. So when you add 10 centigrade with T3, it becomes equal to T5, the hot steam that is entering to the regenerators. Assume both the compressor and the turbine to be isentropic. Determine the rate of heat addition, but we need to find the rate of heat addition, that is Q dot in and Q dot out. Before finding the Q dot in and Q dot out, we need to find the mass flow rate of the gases that is flowing in this cycle. Okay, now come toward the solution. Process 1 to 2, that is isentropic process in the compressor. We can say T2 divided by T1 is equal to P2 divided by P1 into gamma minus 1 divided by gamma. Remember, value of gamma is 1.4 and the Cp value is 0.005. Now just simply put the values and you will get the T2 values. Remember, this T1 is 30 centigrade, convert into Kelvin, that become 30 plus 273 and it become 303 Kelvin. (548.86 Kelvin). Remember, also the maximum cycle temperature is given, that is 800 centigrade, T4. Now consider the process 4 to 5, that is isentropic expansion in the turbine, that is after the heat additions in the combustion chamber, that is T4. You will observe the maximum temperatures and it is given in the statement, that is 800 centigrade. You need to convert that into Kelvin also and it become 1073 Kelvin. Then you can say, now apply the isentropic equations of temperature and pressures on process 4 to 5. Rearrange these equations for T5. Then we can say that T4 into P5 divided by P4, this is P4 divided by P5, so it is the reciprocal of the pressure compression ratio. It is 1 over also there is a conditions in given that T3 plus 10 is equal to T5. Then we can say that T3 is equal to T5 minus, then T3 is equal to . Now apply the energy balance equations on this heat exchanger. So what the energy balance equation said, simply the heat ejected by the hot gases will be absorbed by the cool gases. We can say that Q dot hot is equal to Q dot cooled. So the heat rejected by the hot gases absorbed by the cool gases in idle. I can say that M dot Cp, the temperature of the hot gases, is T5 minus T6 and the temperature difference of the cool gases, that is T3 minus T2. This will cancel out with this. Then the expression for T6 you will get. Now just simply enter the values of T5, T3, T2 and you will get the T6. When you solve this on calculators, you will get the T6 value and it is next to find the work input that is required to run the compressor is equal to Cp, change in temperatures, that is T2 minus T1. Just enter the value and you will get the required work input per kg. When you solve this, you will get the work input to run the compressor per kg, that is 247.1 kilojoule per kg. Work out in turbine, that is Cp, T4 minus T5. T4 is the maximum cycle temperature, that is 1073 minus T5, that is 592.34. When you solve this on calculators, you will get the work output by the turbine, that is 483 kilojoule per kg. Next is the net work out, that is equal to W out minus W in. 483 minus 247.1. When you subtract this, you will get the net work out of this cycle, that is 236 kilojoule per kg almost. Also in the statement, if you see here, the power produced is given, that is 115 kilowatt. We know that the mass flow rate applied with the net work output is equal to the power produced in the cycle. We need to calculate the mass flow rate. The network due is 236 and the power produced is given, that is 115 kilowatt. Divide both sides with 236 and the mass flow rate per second you will get, that is 0.487 kg per second. One thing that has been asked in the question is to find the heat additions and the heat rejection. Now the heat addition is Q dot in, that is equal to M dot Cp, change in temperatures, that is T4 minus T3. When you solve this on calculators, you will get the heat input, that is 240 kilowatt. This was our first requirement. This is answer 1. Next is to find the heat rejection. Q dot out, that is m dot Cp, change in temperatures, that is T6 minus T1. When you solve this on calculator, you will get the heat rejections. So the heat rejection from this cycle is 125 kilowatt. This is the third requirement that has been asked in the statement. This is, let's say, answer